All right, so let's talk about the three main modes of heat transfer. We'll go through conduction, convection, and radiation. So rather than make you write out the full definition, conduction, the first thing we're going to talk about, this is going to cover kind of the first third of the class. All right, so we're going to talk about 1D conduction, 2D conduction, steady state, non-steady state, all these different numerical methods, analytical methods. But you're going to be very familiar with conduction by the end of this course. Okay, so the definition is energy transfer due to interaction between microscale energy carriers within a material. So there's some important words here, right? Interaction between microscale energy carriers. So this is saying you have some solid or some liquid in which the main mode of energy transport is some molecule vibrating or emitting a photon and having it strike the neighboring molecule. Right? So this microscale, molecule to molecule, atom to atom energy transfer within a continuous material. Right? So that's different from radiation, which is at a distance, or convection, where there's something moving. Conduction is kind of a static problem. Okay? So let's dive a little bit deeper on conduction. So what we'll do for each of these is we're going to go through rate equations. Right? This class is ODEs and rate equations. Right? So you'll learn the three rate equations, one that goes with each of these. The first one is called Fourier's law. Right? Fourier, French. Everybody in heat transfer seems to be French for some reason. I don't know. Fourier's law. So this is saying there's a relationship between heat flow and temperature. And that relationship is, for conduction, Q dot double prime, I'll talk about that, is equal to minus K gradient of T. Okay, so this is a very general formulation. What these things are, so Q dot double prime, so remember Q dot is our rate of heat transfer. K is conductivity, right? This is the conductivity, it's a material property. And then the gradient T is basically the operator, the differential operator on temperature with respect to space. So if we were to kind of translate this into a single dimension, so let's think about heat transfer in one dimension only, this would become minus K times dt, d whatever. So in this case, let's pick x. Right? So Fourier's law is heat transfer per unit area, which is the double prime, is equal to minus k dt dx. All right. Maybe it'd be helpful just to write some of this out. So this is, units here are going to be watts per meter squared. This is conductivity. It's a material property, like I said. The conductivity is going to have units of watts per meter Kelvin. Right, and then this is your differential. Okay, so right away you see that there's a relationship between heat flow, Q dot, and temperature in space. This is a theme in this class, right? So don't forget as we go through the class, everything we're doing is relationships between heat flow and temperature, heat flow and temperature. So get that kind of nailed in your head. As we're doing ODEs, it's always heat flow and temperature. Okay, so this is Fourier's law. You might wonder about this guy here, right? So there's this minus sign. Like, why minus? You get that maybe the heat flow is proportional to conductivity. The higher the conductivity, the more heat flow. I mean, that makes sense. Heat flow is also going to be proportional to the temperature gradient. That makes sense. So why the negative? Well, I guess we could think about it for a moment. So let's plot out here. So if I plot temperature as a function of position, if I have heat flow that's in the positive x direction, remember the second law, heat flows from hot to cold, right? I mean, it's intuitive. So hot to cold, you'd have a temperature up here, temperature down here, and we can connect those two. So this is our temperature profile. So if you look at this, right, dt dx, what is dt dx? It's negative, right? So being a negative gradient, that's, by our definition, in the positive x direction. That means it's got to be a minus sign in front of that differential operator, right? So it just comes out of our definition of heat flow as going from hot to cold. Okay. So let's clean up a little bit on the terminology here. I'm using these different symbols, Q dot, Q dot double prime, so on. Let's deal with that. So So let's deal with Q. All right. Just Q, no dot. Okay, then Q dot double prime. All right, so Q is our unit for energy. And so this has units of joule. It is heat transfer. And it is, dimensionally, it's just energy. Right? You'll see what I mean on the second row. So Q dot, that has units of joules per second, or watt, right? We'll call this heat transfer rate. And its dimensionality is power, right? Watts are power. So we'll talk about like thermal power, right? This is maybe weird to think about because you think about like mechanical work as power. There's thermal power as well. It is just the rate of heat transfer in time. And then the last thing is this Q dot double prime. So the units there, as I said, are watts per meter squared. It is called heat flux. Okay, and this is power per unit area. So often for problems, we will solve it as if we're just solving for like some relative or specific heat transfer rate per unit area, and we just express it that way, so that when it comes time to multiply by area, then that's when you get the dimensionality out of it. Okay, so that's the terminology part of it. Yeah. Yeah, so great question. So what you're going to be looking at, it kind of depends on these different modes of heat transfer. So if it's conduction, you're looking at the cross-sectional area that's available for heat flow. Right? So if heat's flowing down my arm, it's the circular cutout, right? If it's convection, you're looking at the surface area. It's the area of the cylinder, right? Same for radiation. So it's going to depend. Okay? All right, so that's conduction. Yeah, any other questions on, I mean, this is like the introduction to these. We're going to talk a lot more about them, right?